Okay, so the source checkpoint. Now that we've got memory all copied over from the source to the target as nearly as we can, we need to do the checkpoint. In other words, we get the final memory state, we make one final pass to harvest all the TLBs and get all the dirty bits. All the page data, all the bits in the bitmap are now sent. We don't leave any behind. And these are sent into the blackout buffer and then formatted actually into messages that will be sent as soon as we bring the migration NIC back up. And then we capture the processor state. For that, we considered using system management mode, but we didn't want to depend on weird stuff like that. So it turns out you can pretty much do it conventionally. It's sort of like a big task switch. So you save all the usual registers, but then we had to find and save basically a bunch of MSRs and other stuff as well. Timestamp counters. And now at this point, we have a consistent checkpoint of the whole source OS in the blackout buffer. Meanwhile, on the destination side, once the source brings its migration NIC back up and pushes its final data through, all the state is now held by the target. And here we're faced with the task of we have to jump from one running kernel into another. This is not a restart of the source kernel. It's more like a hibernation resume. And in fact, if you look at the hibernation code that's in the kernel already, it does a sort of similar thing to this, where they boot a kernel, and then at some point it chops its own head off and jumps into another one. And this is kind of like that system. The first step is we prepare the target, so we resolve this memory overlap. The low 32 meg that was in use by both sides needs to be restored. So we'd be happy to just copy that down from our buffer but the problem is there are some page tables down there. And so we would destroy our view of memory even as we were copying it down. So what we do is we go find all the page tables in the running target kernel that are outside the crash kernel reservation, and we just came out in memory and we copy them into there and reorder them and load CR3. And so now the target kernel is really running entirely inside the crash kernel reservation, except for its own program text. So at this point, when we do this memory copy, we're in our module in basically straight line code, and we never go back to the kernel. We don't use the built-in mem copy. We do it ourselves, and because we're about to obliterate the target kernel text with the low mem buffer. And once that's done, we do the context switch. So the trampoline is a small chunk of position independent assembly code, and we jump to it at the identity map, at its identity map virtual ladder, and run there. And all it has to do basically is restore CR3 and stack and the base pointer, and then we jump back to the saved RIP value in the sync point code. So the sync point code looks like, that was done on the source side, looks like, save all registers and then save RIP, and then basically restore all registers. And of course, on the destination side, we come in from the saved RIP and continue on from there. So we end up restoring all of our registers and returning back out and unwinding and popping and re-adding all devices. So all that turned out to be the easy part. We thought that would be kind of the project, but then, well, we didn't really, but we thought that was the challenge. It turns out the IO device state was the hard part. The problem is the kernel on the source host has these running IO devices. These are real chunks of hardware with resources assigned to them, and the hardware's off busy doing stuff. And now, that identical kernel image wakes up on another machine where that hardware's just not present, or hardware like it is present, but it's not initialized, and for sure it wasn't doing the same thing. So that obviously would be a disaster. We don't know of a good way to capture the hardware state right now. There are these kind of vestigial suspend resume entry points for hibernation, but they don't seem to really give us everything we need. So again, we adopted an expedient solution, which was we remove all the PCI devices. We rip through the kernel's PCI list from bottom to top, basically high to low plus numbers, and just delete everything. And it's kind of drastic, but it really simplifies things because there's no hardware state left. And this actually works. I was kind of amazed that I could could do that and then put them back, and things woke up and kept running. Now, a few kinds of devices need special handling, network and storage. For the network, on the destination side, we want the same MAC address after the migration, but of course it's running on different hardware. The solution we chose to use for that was to make a bonded interface. This gives us a bunch of nice features. The bonded interfaces automatically handle removal and insertion of slave devices, and we can use the MAC getter setting in the ifconfig files to assign a local MAC address that's independent of either the source or destination. One thing we do have to do is we have to take config info, in other words, the MAC address of the physical devices, from the destination host and add them to the source host config so that bonding sees what it was expecting after the migration, because these new devices are going to get added, and bonding has to know what to do with the MAC addresses, how to pair them up with. But you can just do that. You edit the files in preparation for the migration. And meanwhile, the higher layers of the network stack basically they do the right thing. They ride out this temporary loss of connectivity. Tearing down interfaces doesn't make sockets just pop. They just kind of sit there not being able to send data. And TCP and NFS and so on are prepared to resend lost packets and so on in the case of incoming traffic. We have to hope applications don't mind their interfaces bouncing. If you had an application that was watching network interfaces and saw them bouncing around, it could potentially get confused, but we haven't seen anything do that so far. Are there alternatives to this method? Probably. I think, in fact, the MAC address thing was a bit of a misdirection. It could be done without a bonded interface, because really the MAC doesn't have to stay the same. If all of your network I/O to the box is operating at the IP level, the MAC address could change, and nothing would necessarily have to care as long as the ARP tables at the other end got updated. And, IP datagrams wanting to get out would get the new MAC level address and just continue talking to the host even with existing socket connections and so on. But we haven't tried that. Okay. The other biggie is storage. And the problem here is that during the checkpoint, of course, there are no devices. We remove all the PCI devices in preparation for the switchover. And that is going to result in I/O errors, and file systems don't enjoy that. And there would be instant wreckage. So that's a non-starter. For the prototype, what we did was we ran the entire system in an init RAMFS. So we had basically a regular Linux box with an X head and so on. But it was all just running in Ramdisk, and that let us cheat. And that worked great. The real solution we've adopted since then is we switched to external storage, where you could have the root on Fibre Channel, iSCSI, NFS. We chose Fibre Channel. That was the simplest given our development environment. And this seems to work pretty well. What we did was use DM multipathing and configured it to, instead of failing I/O when it loses the last path to a LUN, just buffers it and hangs on to it for some amount of time. And we can do the switchover pretty quick enough that I/Os don't actually have to time out. And then we can, once a new path is added, DM just does the right thing. It discovers a new path to the one it was looking for, and things unblock and go. However, all that wiring depends on user space stuff like hot plug and UDEV, which come from files, which won't be there if there's no I/O. So our hack to get around this really is on the destination we do a quick reconfig of DM, and we've in the LKSM kernel driver, we took a snapshot of the device manager state before, and then we modify it to reflect the new path after the migration, and we insert that immediately after the checkpoint restore. And so DM wakes up without any help from user space, and the right thing happens. It's a little hacky, but for now that's the solution. But the migration does work with a real Fibre Channel. That's basically it for the functionality. We'll talk a little bit about structure of the software. It's pretty simple stuff. the total line count of code is only maybe 10,000 lines, and most of that is in the kernel driver. There are two applications, what we call migrationer, and this is the application that runs on the source host, and it establishes the socket connection with the target side, with the destination, and it controls the overall process and sequences it. And then there's a target application that listens for this connection from the source host, and that's how we get our communication set up. The driver does all the real work. It's a big chunk of kernel code with a handful of different modules for dealing with PCI devices and networking and memory tracking and all that stuff. And that's where all the action is. And then there's, of course, a small build environment because to get this working, we have to have particular kernel versions and RAM disks built for the target environment. And so we need but it's really just a handful of make files and shell scripts. This is a graphical view of basically what I just said. Source host on the left, target or destination host on the right, and the two applications of the bubbles up above the line, which is user space. And then below there's this lksm module that does all the dirty work. And they share the way it's organized is these guys set up a socket, and through a proc interface, they push the FD into the kernel, and the kernel just grabs it and starts stuffing messages into the, we have a small message header and then a payload, and those just get streamed like any other message passing protocol. The migrationer application is a small C program, and it does pretty much what I've already said. Connects to the listening socket on the other side. It doesn't right now, but in the future it would validate the host and the migration parameter. In other words, if you try to migrate from a 64-bit machine to a 32-bit machine, that should fail like right away, and we don't check that. So that's work TBD. And then after that validation is done, it disconnects. Remember I said initially that to get into the target environment, we have to reboot into the special kernel. And then this migration application reconnects to that new target environment, and then hands control over the kernel module. And there's a sequencer built into there that rips through the memory tracking, brownout, checkpoint, blackout cycles, and device removal, and all that stuff. The target application is an even smaller C program, and it listens for connections. The way we get the, in the target environment on the destination host, we would like a kernel running that's very similar to what we're running on the source side. And the way we get that is we pack up the migration application on the source side, reads the source kernel from /boot, and it makes up a RAM disk. And actually the RAM disk was made by the build environment, so it's sitting there waiting for the application to read it. That gets stuffed through the socket and read on the destination host. And the target application writes those into files, and then it kexec's them. And this is how we get into the crash kernel reservation with a compatible kernel running on the target side. And then the target application is part of that RAM disk, and so it wakes up, it's basically SBIN and init. So it wakes up and waits again for the source to connect, and then it jumps into the kernel. So the kernel module itself is invoked from the applications through proc, and they pass in parameters, things that are easier to do in user space, all the socket marshalling, looking at host memory sizes and stuff, and storage configurations where the application will do that, and they push it down into the kernel through simple commands. And then in the kernel, we use the same driver on both sides, but there are, because a lot of this stuff is kind of library code where we need it, in the both category is sync point code. We need to be able to save and restore CPUs. We need to be able to do PCI device management, network device fix-ups, storage fix-ups, all that stuff. And a few things are special to one side or the other. There's the sequencer that controls the phases of the migration. That's on the source side only. And there's the message handler that responds to commands coming over, and that's on the target side only. But these are this list here is sort of the main modules that make up the driver code.